Everybody, in the last class we got introduced to digital to analog conversion and we discussed weighted register based DAC and binary ladder based DAC. In this class we shall look at some other important aspects of a digital to analog converter circuit. In this we shall see that why we need to use a buffer amplifier and what sort of buffer amplifier we use for a DAC circuit. And there will be, other than buffer amplifier, there are some other additional circuitry that will be required for a full fledged DAC operation. And if there are multiple signals need to be converted to analog, then one possible scheme that can reduce the number of DAC that is required for the conversion. And we shall discuss some of the performance issues here, and more performance issues we shall take up when we discuss ADC. Together with ADC we shall look at them, okay, and then we shall look at one practical IC, okay, that is DAC 0808. Okay. Now, in the last class towards the end we had seen that the ladder based DAC, which is more preferred compared to weighted based register based DAC. So, in that ladder based DAC, depending on how you terminate what is the the load, the output voltage becomes different, isn't it? So, with 2R termination we had certain voltage, with very high input, very high resistance termination, some other voltage which is close to full scale voltage. Okay, but if the different if the load varies, then the voltage will vary, right. So, if in such situation with variation of the load, there could be a misinterpretation of the digital input that is there. Okay. So, we need to have an arrangement by which the variation in the load should not affect the analog output that is getting generated, and for which we think of putting a buffer circuit, and also if amplification is required. So, buffer amplifier is that can be put at the output of a ladder. Is it clear? Okay. So, we do, because with loading effect if the voltage changes, we have seen that, isn't it, that then what was the corresponding digital input, that part will not be very clear. Okay. It could be considered that some other input was there. So, the integrity will be lost, right. So, this is what is our consideration at this point. Okay. So, buffer is an intermediate circuit that isolates or separates one circuit from the another. Okay. So, the circuit that we discuss here is a operational amplifier op amp based circuit, and here it is connected in a non-inverting mode, right, and this is a unity gain, right. So, this provides a very high input impedance and it does not load the circuit, and whatever is the input here, the output will be at that side. Okay. And this is what I was telling, that this output voltage which changes with the load, that part we want to avoid. Okay. Now, there could be another circuit, this is inverting non-inverting op amp. Okay. So, it can be used for using inverting mode op amp also. So, for which we can have a circuit like this, right. So, this is the op amp circuit, this side you can recognize, this is the ladder network, right, and this MSB, right. So, MSB produces a current. So, V by 2 is the effective voltage, Thevenin voltage, and divided by the output resistance which is R. So, V by 2 R, and here in this case it is V by 4 and resistance is R. So, the current produced is V by 4 R, and similarly it will go on, right, V by 8 R, V by 16 R, and so on and so forth. So, this is the current that is going in this direction, right. And since it is virtual ground, it is not actual ground. So, this current will get diverted over here, okay, isn't it? That is how op amp works. So, again you have to review your op amp theory, or otherwise remember this specific aspect of op amp being used in non-inverting in the previous case and inverting in this particular case, how they work in these two modes. Okay. So, the output over here, this is the final analog output, will be this minus R times, because it is inverting amplifier, multiplied by all the currents, okay, all the currents, right. So, accordingly it will get minus V by 2, minus V by 4 and so on and so forth. So, if you add them up, you will get the equation that we had got for the DAC. Now, we have got a buffer put in between using an op amp. Is it clear? So, this is used at the output of the ladder, fine. But that is not all. There are more things that are required for a DAC to work. So, these are additional circuitry. So, let us see what are they. So, what you see over here, to begin with, let us consider that these are some flip flops, okay. So, this is actually a resistor, right. So, this register as many number of flip flops, as many number of bits that you are looking for conversion from digital to analog, okay. So, here 4 bits are shown, but it can be extended to n bits. Is it clear? Okay. So, this register stores the digital information, right. So, as long as it is not gated, I mean input is not changed, so the output is remaining true. So, the value is not changing. Okay. This is important that output remains stable. Okay. So, based on this value, this is high or low. So, this precision voltage source and level amplifier holds a value at its output, which is a very precise voltage of say 0 volt or some higher voltage, in this case say 10 volt, okay, when this digital to analog conversion is happening. It should not change, okay. It should remain true for this DAC conversion, otherwise the output will be something different from what the digital input is. So, this digital data is shifted here, held, and precise corresponding these binary outputs, voltage levels are placed at the input of the ladder, and this is your final VA, and this VA will go to that buffer amplifier that we have just discussed. Is it okay? So, this is required for proper conversion. This is required for proper conversion, so that the voltages do not change when the DAC conversion is taking place. Okay. So, to maintain the integrity, right. So, this is the job of the level amplifier, that signals presented to the ladder network are of same level and constant for low and high. So, all of them. So, it should not be one is say 9.8 volt, another is 10.1 volt, is not like that. So, small variations in the circuit, that is not. So, this is needed to be ensured. Okay. Now, the digital data is coming over here, right, and this digital data is shifted, okay, or read, I mean when a particular strobe pulse is there, otherwise it will remain at 0 0. Okay. So, the value will this registered output will remain the same, it will not change. Only during the digital input is established, okay, then only a read in strobe pulse will come, and that input will be passed to the shifted to the register, okay, and following that it will be held till the next read in comes, read in strobe comes, and then it will be getting converted. So, this also is useful for avoiding transients or maintaining the integrity. Is it clear? So, this is also something, the gating that is required, and these are all AND gates, you can understand that how it works. Is it fine? Right. Now, a settling time is required between data shift, so that is getting data shifted, and data read, okay, for this particular flip flops or the register that is there, right. And once it settles, conversion is done, I mean and then you can read another data. So, this is the primary factor behind the maximum rate of conversion that is possible using a DAC. Is it clear? because there is a, for this particular registers or flip flops that is inside, there is a finite rise time, finite fall time. Okay. So, these are need to be considered in deciding the maximum rate of conversion of a DAC. Is it fine? Okay. Now comes if you have multiple digital input lines, right, and you would like to convert to analog signal, right. So, you can have as many number of DAC, right, and whenever you are reading it, then the flip flop register output will be holding it, and then truthfully, and then the output will be available, and the next read in comes, again it will be getting converted, the output will be held. So, that is the way it will work. But if you want to save on cost, or if you see there is an opportunity of multiplexing, okay, the time intervals by which you are reading the input signal is such that within that period you can convert another digital data to analog and come back over here, okay. Then you can think of using one DAC to convert multiple digital input signal. Is it fine? Okay. So, but in this arrangement we need some additional circuitry, we are discussing that part over here. Okay. So, what is it? So, this analog output that is coming for a particular channel, right. So, this is the digital input lines. So, this is the DAC converter, and depending on whether it is channel 1 input digital input 1 or input 2 or input 3. So, you are you are taking this output to one of them, right. So, next time it is converting another channel. So, it is over here. Now, what happens to this one, this signal? Earlier, if it is one dedicated DAC, this signal was held by the registered output and the buffer, this amplifier, this level amplifier. Am I clear? So, let me go back and so this is the level amplifier which is holding it, this is there, right, if it is a dedicated DAC. But if it is not a dedicated DAC, once it comes over here, what will happen to this input, this output? Okay. For this we need a sample and hold circuit till it comes back and reads the same digital input signal and passes to the output. Okay. This is the necessity of having a sample and hold circuit if you are trying to decode multiple signal digital input signal using one DAC. Is it clear? And for that, what we use at the output of it, this is the the buffer, right. After that, you are putting a op amp, and this is a capacitor. So, this is a sample and hold circuit. So, this is getting sampled, this is the sampling that is part that is being shown here, and this has got a very high input impedance for which the capacitor will be discharging very slowly. So, the output will be more or less remaining same till the next sample comes, okay. But it need to be adequately fast, okay, so that it does not leak appreciably, as though the impedance is very high. So, RC constant will be very high, but still we must ensure that it does not fall to that level that the integrity is lost. Is it okay? And the sampling rate depends on capacitor, how, as I said, quickly it discharges, or the voltage comes down, and frequency content of the analog signal, that means the analog signal that is produced. Okay. So, there is something called Nyquist rate. You need not worry about it unless you already have an exposure about digital signal processing, that if frequency content is a bit higher side, then you need to sample it faster, and if it is frequency content is less, that means slow moving signal, you can sample it at a lower rate. So, that is the idea. Okay. right. So, now we come to something which is related to performance issues of a DAC. Okay. So, there are more aspects regarding DAC performance which we shall take up when we discuss ADC, because certain things are common, right. So, we shall discuss them in parallel, right. So, we shall take it up when we have a introduction to analog to digital conversion in subsequent classes. Okay. So, important things are of course, accuracy, right. It is a measure of how close is the actual value to the theoretical value. Of course, this is one important element. It depends on the precision resistors and the reference voltage supply, which we mentioned that why that particular block and additional circuitry required. Okay, or required. Okay. Next is resolution. It is the smallest increment in the voltage that can be recognized. Okay. So, this is associated with the LSB, right. It depends on the number of bits in the input digital signal. Okay. If the number of bits are small, less, okay, then of course, the LSB related the value will be small. If the number of bits are more, then it will be 1 upon 2 to the power n or 2 to the power n minus 1, okay, depending on whether it is ladder based or a weighted register based. Okay. So, these are the two important aspects, and though it looks a bit independent kind of thing, but there is certain relationship between them which we can see in these two examples. Okay. So, if it is a 4-bit ladder and if it is a 16 volt reference voltage is there, okay, just for quick calculation, it could be some other voltage also, and accordingly you can calculate it. So, resolution will be 16 by 2 to the power 4, that is 1 volt. Okay. And if you are looking for an accuracy, say 0.1% using precision resistor, amplifier and all those things, then this is 16 millivolt. Okay. But between one level to another level, it is 1 volt, that is different, that is there. So, this is a bit on the higher side, it is a bit overkill, right. So, you can use more bits to improve the resolution, right, or even less precise components will do, okay, because the resolution and accuracy they are quite apart. And consider the other case, say 11-bit ladder and the reference voltage say 10 volt, okay, then the resolution will be 10 by 2 to the power 11, this is 5 volt. And if the components that I have used and all gives an accuracy of 1%, right. For 10 volt reference voltage accuracy is 1%, it is 100 millivolt. So, you are trying to measure signal at 5 millivolt interval, that is the resolution, but the accuracy is is so low that it is 100 millivolt, that could be a difference. Then what is the point, isn't it, to go for such a high resolution? So, either you improve your accuracy by using more precise components, or you can reduce your the number of bits because it is not required. I mean it is again from that side, that point of view, it is overkill. Okay. So, these are certain things, and as I said, they need to be considered together, and accordingly the DAC design is to be done. The other important point is when you look at a DAC, is called slew rate. So, the maximum rate at which the analog output value of the DAC can change. Okay. So, it depends on the working of the output amplifier, that is the op amp. So, how quickly the output can change. So, if you can change the input, right, from a low value, say 0000 or 0001 to a suddenly a high value, say 1111, but how quickly the output will change, that depends on the slew rate of the op amp. Okay. So, that is also an important measure. Right. Now, when a DAC is made, so often we consider monotonicity test. Monotonicity test means monotonous, it is increasing at the same rate. So, gradually it is increasing. So, that is what we need to see. So, if it is the digital input is gradually increased, okay, so the corresponding analog input should increase in this manner. Okay, these steps are because of it is say 1 volt, 2 volt, 3 volt, like if it is a 1 volt resolution is there. So, that is how it will go, or if it is a 1 millivolt resolution is there, 1 millivolt, 2 millivolt, 3 millivolt and so on and so forth, depending on your digital input. If your digital input is increased in a continuous manner, one value at a time incremented, then the output should increase in this manner. Is it okay? This is the one, this one is what is the correct output, right. But if you see the actual output is something like this, what you see over here in the bold line, then this and this can be observed using this monotonicity test. Okay. So, then there is some issue, some problem somewhere. Okay. So, this test it will give you. Okay. Right. So, it checks if the analog output voltage increases regularly with the increase in digital input. So, what kind of issue could be there? So, for this particular example you can see, so this is the blue line. So, this is 0011, after that it is increased by one value. So, it should be 0100. Instead what you see over here is 0000, right. So, that means there is some issue with this particular bit. Okay. Similar thing we can observe over here also. So, second MSB there is a problem. So, this is a 4-bit second MSB problem, and it could be problem with the AND gate or the gating of it or at the amplifier, or some issue is there, and accordingly you have to resolve it. So, this is coming from monotonicity test. Okay. Another test is steady state accuracy test. It is known digital number to the resistor that is given, and you measure the analog output voltage with a steady accurate meter and compare with the theoretical value. Okay. So, that is the accuracy that we have already talked about. Okay. So, these are important things that you perform. So, one example we take up is a practical DAC 0808. So, from Texas Instruments this data sheet. Okay. So, this particular DAC is 8-bit digital to analog converter. Okay. And you see over here it is written in this manner, these are the digital input A1 to A8. Okay. So, this is that is the way they have mentioned it, but you can have a different kind of nomenclature. LSB could be A0 and it could be A7 and so on and so forth. Okay. Now, the other things that you see over here, these are the power supplies, okay, 5 volt minus 15 volt. The settling time, I told that these data read, okay, through the gating, that read in strobe, and the resistor, the transients, rise time, small time, all those getting settled. So, next time again you can read the data, that settling time is important. So, that and it also gives a maximum rate of conversion, okay, is the primary factor. So, this is your 150 nanosecond, okay, for 0808. Slew rate, I said how quickly it can change, the output can change based on following a change in the input. It is 8 milliampere per microsecond. Relative accuracy has been found to be 0.19%. Absolute accuracy, it will be coming from the reference voltage and other things. Output voltage range at pin 4, okay, is small as such, minus 0.6 volt to plus 0.5 volt, but actually what it gives a particular range of current, and when you pass it through a amplifier, at the output the voltage level will be different. So, that we shall see through an example. So, it is output current at pin 4, which is of importance to us, which makes more sense, which is 0 to I reference. So, I reference is coming from here. So, this is B reference and this is R reference. If you divide by them, okay, so this is connected from outside, then you get I reference. So, the current, the change is from 0 to I reference based on the digital inputs, okay, and this I reference will come through this resistance, and accordingly the output voltage will be generated. So, this particular output voltage is not of much concern, but the output current that is varying because of the digital input, okay, that is of importance for this particular DAC, okay, and after that there will be a amplifier like this, op-amp based amplifier, fine, right. So, we look at how it works, some example. Okay. So, in this arrangement we had said that A1 is the MSB, right, and A8 is the LSB. That is how it has been mentioned in the data sheet and all. So, but we know that if a different kind of nomenclature is used, A0 to A7, A0 LSB and A7 is MSB, then we can just need to change the naming of it and the things will work out. Okay. So, we need not get confused with A1 and this B1 their association. So, here A1 is MSB and A8 is LSB, fine. So, this is what we had seen before over here. A1 is MSB, right, A1 is MSB and A8 is LSB. So, accordingly it is being worked out, right. So, I reference is V reference by R reference, very clear, right. So, I naught will be I reference multiplied by whatever you are getting from the this thing, this input digital input data. So, this is V naught is I naught into R, okay, that at the output amplifier. So, V naught is equal to V reference by R reference, this digital input converted to your corresponding analog unit analog output in the ladder network and multiplied by R. Is it fine? So, finally, V naught is equal to, if R is equal to R reference, so V reference into this one. Is it clear? So, this is your the corresponding DAC analog output depending on the digital input that you place in the at the input side in A1 to I mean A8 in 8 bits. Okay. So, if all digital inputs are 0, okay, so these are all 0 value. So, V naught will be 0 volt, right, and if all digital input are 1, okay, then the output will be 255 by 256 into V reference. So, 0.996 into V reference, and if it is V reference is 10 volt, it will be 9.96 volt. Is it okay? Fine. So, this is how your DAC works. So, with this we come to the conclusion of this particular class. So, what we have seen, that buffer circuit is used at the output of the ladder not to load the network and ensure integrity of output voltage. Op amp in inverting mode and non-inverting mode can be used as a buffer circuit, and we need additional circuit for a DAC which involves resistor, level amplifier, getting to shift digital input to register, all these things, and that makes the DAC fully functional. Okay. Settling time required between data shift and data read primarily decides maximum rate of conversion. Okay. And sample and hold circuit is useful when conversion is done for multiple channels using one DAC. Okay. Accuracy and resolutions are important performance metric of a DAC, and the tests we have seen, monotonicity test, steady state accuracy test, these are the kind of test that we perform, and to figure out if there are any issues in the conversion. Slew rate gives maximum rate of change of analog output, and this is also an important quantity. Okay. And we also discussed one practical 8-bit digital to analog converter, DAC 0808, and we found how it is useful in converting a digital input to corresponding analog equivalent. Okay. Thank you.